Okay, it's my pleasure to introduce our next speaker. Jason Corso is a professor of electrical engineering and computer science at the University of Michigan, and also co-founder and CEO of a computer vision tech startup called Voxel 51. And his research focus throughout his career has been on kind of exploring the relationship between natural language and robotics and computer vision, with important contributions in video understanding and action recognition. And he previously served as director of the Stevens Institute for Artificial Intelligence and was an associate professor at SUNY Buffalo, where he supervised my PhD. So welcome, Jason.
Thank you, Jeff. It's a pleasure to give this virtual presentation at this interesting workshop that you're organizing. I'm going to assume, since you've quieted down, you can hear me, so I'll just continue. So great. So this is a talk that is, I think, maybe a little different than the other kinds of talks in the workshop. It also involves a majority of, or half at least, of unpublished, very new, very risky work. But I figure at this point in my career, I don't know, you can read my papers already out there, but you can't see what the lab is working on now. So that's primarily what we're going to talk about. And then at the end, I'll tell you a little bit about Voxel 51, which I hope will be interesting too. So the title of the talk is toward a thinking cap-like system that can guide humans in novel tasks. And the real focus of the talk is to explore where we've been in computer vision, machine learning, robotics, and this inundated world of data, the like data deluge, and how all of our models expect so much data to train on, and instead kind of understand what the human role is in that process, right? Like with lots of data, the human comes in to maybe label the data initially, and then kind of exits and is a consumer of the tool. And you can see like these data sets have been growing like gangbusters for the last few years or decade or more. Language on the left side of the slide, video data sets on the right side of the slide. There's just huge amounts of data, and it does enable amazing capabilities when you can capture all of that data and go and create, for example, interesting renderings, like this GAN-based system that is changing the actual actor in these videos, right? Like, this is not my work. This is just off of YouTube, but just so interesting where you can go with data. But I think we should be asking ourselves, what is the actual value in sort of putting asking the human for input at only once, setting them aside, and then expecting humans to be AI systems to be fully autonomous. Right? Like in what situation does a kid operate without a teacher or a parent, right? Like they learn through so many iterations. And even me, myself, like in my startup, for example, I collaborate with the 20 other employees in the company all the time. There's a lot of interaction. So why aren't we thinking about interaction between humans and AI more often in our field? And even importantly, there are very distinct differences between AI systems, which are very good at redundant, repeatable tasks that are kind of boring, such as object detection in video frames. Whereas humans are really good at adaptable, on the fly, off the cuff type situations where they need to process multimodal inputs, make decisions quickly with limited prior knowledge, and extrapolate. In this case, right, like for example, if I wanted to ask any of you to find the snowman with the red scarf in this image, it really wouldn't take you that long to look at it or to find it. It's all the way, it's in the center back there. But if I actually just gave that same direction to any modern computer vision system, it would not be able to do it, right? It had never seen that type of snowman that's that small in this cluttered scene, yada, 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 right? So my lab has really been focusing on a notion of hybrid intelligence that attempts to integrate human systems and AI systems during the full life cycle of computational interaction or computational systems. So I'll give you a couple examples of this, kind of where we've been. That is indeed published work. Then I'll go to what we're working on now, right? So this one example is from an ICCV 2017 paper where it's really kind of like human in the loop inference, right? So imagine you have to estimate the 3D vehicle pose from a 2D bounding box of a vehicle. The actual backdrop to this problem is something like car accidents happen only every something like 100 million miles driven. Like fatality type car accidents happen only every 1 billion miles driven. That's very rare. Like any type of car accident is a rare event. No, like Waymo, whatever, Tesla, like they can't drive that many miles. So they have to use other sources of data. A potential other source of data is YouTube, in which there are billions of miles being driven globally, and people are uploading these videos to YouTube, but they're all from dashboard monocular cameras. So the idea would be, can we reconstruct the kinematics of the vehicles in the scene and use that to drive simulations and so on. Okay, so there's a method that we adopted called the render for CNN that can take such a bounding box as the blue one you see here and do a relatively good 3D pose of that from a 2D image. This is all based on DeepNet. I'll give you the network in a second. However, in the situations of interest to this particular problem, the vehicles we're talking about were all in car accidents, or many of them in car accidents, so they were all damaged. And there wasn't any damage seen by the computer vision system during training, by the render for CNN system during training. So the pose was completely wrong in many of these situations. Right, so we had this notion, right? So like input image, get some image features through like AlexNet, tack on some pose estimation, regression, prediction layers, and oh no, we have a bimodal distribution on the output. That's in particular, it's not sure if this particular vehicle in this bounding box is facing forward or facing backward, and which is plausible, in a system like this because it's not integrating any priors. But what we'd like to do is ask the human a question, right? This is not on the fly. This is not in the vehicle. This is building a data set to help go train a better autonomous driving system. What if we asked ourselves, the research question is, what if we could ask the human only one question, like, give me one feature point, could that help the AI system? In this case, we ask for, for example, click on the back left wheel, generate features from that, integrate that with the standard computer vision CommNet, no human involved, and we turn the bimodal distribution into a unimodal one, right? Like human in the loop inference to go and facilitate more direct interactions, because humans can adapt to this type of interaction. Concretely, and we don't have to go into great detail here, the render for CNN method is up at the top here. It's AlexNet, followed by a two to three layer regression system where you are actually doing the prediction, right? What we add is this key point network or layer or sets of layers that we call the click here CNN, in which the key point location and key point identity is transformed into a CommNet usable or renderable system that ultimately acts like a spatial attention mechanism at a mid-convolution layer. Now, empirically, we went through, modulating COM4, COM3, COM5, and so on. And the one that I'm showing you here is just the one that in testing ended up working best. And this leads to truly concrete improvements in pose estimation accuracy on the standard metric from the render for CNN paper across the entire data set. What you could think of is basically you're looking at the top row of this table and the bottom row of this table, right? So for buses, cars, and motorcycles, we're seeing an improvement from 4%, 12%, 4%, or 3%, on average about 6%, right? In all cases, it tends to operate to convert a multimodal distribution into a unimodal distribution, independent of the type of scene we're looking at. Right, awesome. So that was example one. Example two interacts with humans and AI in a little different way. So the context in this problem is there is a human available to give you some input, some annotation, much like in supervised learning, but let's use that annotation to modulate a method that's trained adaptively on the fly to then go and ultimately do a video object segmentation to then go and remove an object from video like you're seeing here, right? Like input video, one frame is going to be annotated by humans, and then we have some off-the-shelf method that will remove that object throughout the video from the scene. this problem is called video object segmentation in computer vision. It's not a problem that we created, or maybe like a decade ago, maybe when Jeff was in the lab, like we were kind of creating aspects of this problem actually, but other people created this challenge called the Davis challenge around video object segmentation. And basically you train on some images like ImageNet, then you take a parent network that's actually trained on segmentations, like full frame segmentations, which is great, or full frame object segmentations. And then the key is that at test time, at inference time, there's a human available, you ask them to give me the segmentation for one frame. And the idea is that this test video has not been seen in this parent network training data set, right? So it might be something completely different from from like not a bus, not a dancer, but maybe a break dancer, like you see here, right? For example, in the off-the-shelf method or off-the-shelf challenge, the first frame is given, always the first frame of the video to ask the human, i.e. the community didn't ask the question, is it interesting to decide which frame of the video we should ask the human for? And we realized through some analysis that indeed it does vary, right? Like you could ask them for the first frame, performance might be one way, next frame performance might be another way, or the last frame, maybe the performance improves greatly. Right? There's a lot of methods on here. And right, so we asked the question, is there a better candidate frame to get that input from the human? Okay, so just quantitatively, here's some analysis, right? Like the vertical, the chart at the bottom of this slide here is giving you the standard sort of Jacquard measure on how well the ultimate video segmentation performs if you ask for, say, the first frame in annotation. If you ask for frame 12, it improves a little bit. In fact, this is the best case for this particular video. Frame 20, worst case scenario, just the the context of the video. Last frame, roughly the same as the first frame in this example, right? So so we wanted to figure out, like, is there a better way to ask for a different frame input, right? So we want to use the annotation and annotator's time better. The challenge with this data set is that there are only 4,200 frames in it. That's just not enough. There's too much variation in the videos to go and actually regress like 1 through n, which frame you should ask for. Obviously, we tried that first and it failed miserably. So our idea here was instead to think about using pairs of frames. So that would get n squared. So 4,200 squared is a lot. Still didn't work too well enough. What we ended up doing was actually using n squared plus k, where k is 3. And those 3 frames are just used as context, right? So we have this network where the first frame, the second frame, and then 3 other randomly selected frames, right? So this is a huge amount of possible training data, are just passed through an embedding with ResNet 50 and then through 4 layers of a fully connected network, right? To actually do a swapping, like it's kind of like a distance function or like a ranking function, which frame is better than the other frame. And that's why the method's called BubbleNet. This was presented at CVPR 2019, right? So we take that, this is the input frame, same type of graph you saw on the bottom of the other graph there. And ultimately we're able to rank sort the frames and rank them roughly. It's not exact because this is a deep learning based method, but it does get a good frame near the best one to ask for more frequently. And so here in this particular case of the video on the left that I'll start playing in a second, frame 54 was the best one. And when the human actually gives us that segmentation, you'll see when you compare asking for the first frame versus asking for the 54th frame, wow, the segmentation is just that much better. Right, so we simply asked, could we use the human in a better fashion? And the answer is a resounding yes, both visually and quantitatively. So there's not too much time in this talk, but we kind of quickly run through like higher's better in the first 2 columns, which we can focus on here. First frame is like 113. Mean performance with hours 125, right? Random is 116, which is actually better than the first frame, right? So you could have done random selection and done better than the first frame, right? So interesting. And the best is just an upper bound. If we just went through every possible frame of the video, choose the best one for every test video, that's what you'd get. Awesome. So now this is what we're working on now. This is like kind of hot off the presses, really exciting work that is part of a program at DARPA called the Perceptually Enabled Task Guidance Program, in which we have a project. But just again, to warn you, this is all preliminary, unpublished. I mean, I stand behind it. I know what's going on there, but but all pretty new work, right? So in this particular work, the idea is let's take an augmented reality environment with a human wearing a device. I'll show you a couple of devices we've built already or use already, and watch them do a particular task, such as making a peanut butter and jelly sandwich. Sounds easy, really hard. You'll see why in a second, I guess. And then if they make mistakes when they're doing that task, help them out. Give them some guidance. If they ask for help, help them out. Tell them what's next, right? That kind of interaction is what this project is all about. This is a collaboration across 4 different universities, and it really integrates this notion of like a dynamic atomic task space that's learned by initially reading recipes and watching YouTube videos, that has kind of a referential data store that's activated on the fly when the AI system is watching the human do something on the fly, and then a novel amount of sort of language and visual-based AR communication with that human to kind of guide them through the effort, right? And so again, this is again the PTG program at DARPA. Really, this is all about peanut butter and jelly. This has been a problem in my lab for about a decade now, just trying to figure out how do you actually model tasks from videos in a way that can render like grounded understanding of content while also having AR-based abilities to kind of understand what's happening, interact with humans, or guide robots and so on. One might think, at least the Americans here think peanut butter and jelly is like, it's old hat, it's easy, right? You get 2 slices of bread, spread the peanut butter, spread the jelly, close the bread, slice it in half, you're done. Easier said than done, right? In the real world, there's so many variations, right? If you actually go to YouTube, type peanut butter and jelly recipes or videos in it, you will see people putting bananas on their peanut butter and jelly sandwich. What on earth is a banana doing on peanut butter and jelly? If you ask kids, is it put the jelly first and then the peanut butter? Or the peanut butter first and then the jelly? I never even thought to do this. More actually say jelly should go first. Blew my mind as an American. Or you can even go to Smucker's and buy a jar of already mixed peanut butter and jelly, so you're only spreading once. The dynamic like variability in what this problem space is, it's just really interesting as a computer scientist. So we're working in like this in the cooking domain in this project. In this domain, we have 3 types of recipes. One is pinwheels, which is essentially peanut butter and jelly. It's like peanut butter and jelly on tortillas, and you roll it up and then cut it. And pinwheel, then coffee is like a pour over coffee, and then mug cake. You can just see some examples here. But and like our annotation protocol for this problem right now, it's very simple. We just want to detect through this AR system, when is a human making a mistake? Okay. We've got a lot of videos, done the annotation on them. And even in this simple example, like we have 4 labs doing this data acquisition, the variability is resounding, right? Like people put ingredients in different locations, they do things in slightly different orders, or they interpret the instructions very differently. It's just really an interesting problem, right? So our actual system is built on we have 2 systems, one that is built with a tactical helmet, and then a webcam called Amiibo, which is wirelessly connected to the system. The second system is using the Microsoft HoloLens 2, that has a challenge in that the field of view for the HoloLens really doesn't work for this problem, right? So we didn't like kind of realize this off the shelf, but the program wanted to use HoloLens. Many of the teams were. That's why we're playing with 2 different systems here, right? And so in a software sense, it's all sort of Python-based, multiprocessor system-based, which was more software engineering than anyone in my lab has ever done. But it was fun. I like software engineering. It's good. Why don't we skip over that? Like just going over this quickly, like very classical ideas here. Like, so frame-based evidence to do state estimation, like where you are in the recipe. And then we have an HMM-based model for if you've made a mistake, like in the ordering of the recipe steps, right? So take a resonant embedding of every frame, connect that to a process-specific HMM, and then do inference on that. Works fairly well, right? So in the 90s percentile, maybe that's not good enough actually to be used in practice yet. But you can kind of see, this is just a video of the tortilla being made, or the pinwheel being made. Place tortilla is the first step. They get the tortilla out. They go and spread the peanut butter. The words here, this is a test case, and the words here is just what the system thinks is the next step. I'll just skip ahead here since we're low on time. Yes, DARPA has fed my lab students for the last 6 months, a lot of peanut butter and jelly and coffee. But you get the idea. And I just have examples of the other slides as well. And then again, like we want to be able to detect when there are mistakes actually being happening here. Like you do the, in the video you'll see next, actually what's going to happen is that the user will, I think, try to spread the jelly first instead of the peanut butter, right? So this is very specific here. This is actually a physical recording of the device in the lab. Right, they go to the jelly first, right? So that's a mistake. Another type of mistake is if you spread the peanut butter first, and then instead of spreading the jelly, you immediately roll the tortilla. Oh, maybe not. I don't know what the mistake was in this video. Oh, I get it. So instead of, he forgot to clean the knife, right? So the recipe, the protocol, which is more than a recipe for this DARPA project, is very specific. You got to clean the knife after the spreading the jelly, and he forgot to do that. All right, so we're basically out of time here. Really, thanks for your attention. Kind of went fast through this journey. We could talk for days about this stuff, but you know, in my view, I think that the key question to be asking at this time is really how should cooperative cognitive systems be specified, be understood, be analyzed, so that humans and semi-autonomous or humans and agents can work together more effectively. And just before I end and take questions, just wanted to note, right, just a side note, I do have a startup company. It is called Voxel 51. We make an open source, fully free, get the full ML stack, not selling anything here, it's a tool called 51. It is a massive Python library for data set curation and analysis, and this really amazing GUI that allows you to interact and touch your data, again, put the human in the process of analyzing data more than has been for the last decade, in a way that will speed up your workflows around images, video, and 3D data. It's been downloaded about 400,000 times and has about 150,000 active users right now. So I'm happy to answer questions offline about that if you're interested. And I would wholeheartedly appreciate a GitHub star if you go to github.com/voxel51/51. So thanks very much. Happy to take any questions.
Any questions from the audience, the live audience first? If not, I have a quick one. So presumably DARPA isn't particularly interested in making peanut butter and jelly sandwiches. Do you see any significant challenges in generalizing the approaches that you're developing there for these sort of the recipe domain towards other tasks?
Yeah, it's a good question, Jeff. So there is a lot of variability in different domains. And I actually, on this laptop, I don't have a video, but we are working with BBN, who's another performer in the program, in a battlefield medicine type application, right? Like splinting a leg or putting a tourniquet on or doing other operations. Actually, we've been able to generate, since the system is fairly sort of autonomously learned, if you will, right? There's not like a lot of human parameter setting. It works as well in that domain currently as it does for the cooking domain. But I mean, you know, thinking about it realistically, there's so much variability in like real world sensing and like even just the problem that we have in this project, which is like real time sensing and inference. That it will be a long time before like this is a done deal for sure.
Do we have a question?
Just a quick question. Are you considering adding other sensory data to your logic that you've written here, just like force feedback, that kind of stuff?
Yeah, it's a good question. So well, when we use a HoloLens, we actually use audio and both like RGB high def video and grayscale video and the depth channel. We are considering like an IMU on the head, for example. Wearing gloves might be a problem only because of the ultimate domain, like Jeff's question, right? Like, I'm not sure if in practice there are many sort of force-based gloves being worn, but yeah, I think one should use whatever sensorial input or data stream is most relevant to the task. So we are indeed exploring other options for sure.
Great. Thanks for the question. And Jason, thank you for the answers. I think in the interest of time, we need to move on, but let's everyone thank our speaker.